So I have here an example web application that you can use to race birds. Just pick your favorite birds, click on race, and see who is the fastest. In the backend, it's a Java application. The Java runtime has been instrumented with the OpenTelemetry Java agent that is collecting the monitoring telemetry and sending to the Splunk observability backend. Now, we use this application to demonstrate memory profiling. So we've implemented the stopwatch here in a way that creates many objects. In fact, the number of objects that we create is so big that if I had several users use the same UI simultaneously, then the JVM garbage collection process would have a hard time keeping up with allocation. And it would end up using most of the CPU resource, and the actual services running this application would become really slow. Now, if this happened to your production Java services, then you would definitely want to understand where in your code do you have the bottleneck that is responsible for all of the excessive memory allocation. And to find that out, you would need to switch to your Splunk observability account. I'm looking at the always-on profiling screen here, and as you can see in the heap usage chart, when I started the race, then the heap usage started to climb up. At some point, garbage collection kicked in, started reclaiming memory, freeing memory, but when I started the next race, then memory usage went up again. If you look at allocation rate, then the yellow series here will show you that at times allocation exceeded even 1.5 gigabytes per second, which is huge. Now, how do I know where in my code do I have the line that is responsible for allocating so much memory? If I zoom into the time period when allocation was the highest, then if you remember in the previous slide, I explained that our instrumentation captures a stack trace every time there is a specific TLAB memory allocation event. So in the time range that I just selected, our instrumentation has captured close to 400,000 stack traces or call stacks. Now, this is a big number. I wouldn't want to flip through all of these call stacks one by one. So instead, I will look at the flame graph chart that you will see here down on the right-hand side. How do you read a flame graph? The wider the boxes, the more memory the specific parts in your code allocate. So if you see here, this section of the flame graph, if I hover over here, I can see that it represents 95.2% of memory allocation. And if I look at the last element here, you'll see that the method that is responsible for this excessive memory allocation is the value of method of the long class. But where in our code are we using this method? If I scroll down here to the end, I can copy the whole stack trace, and now when I switch to my IDE, I can look up the analyze stack trace feature. I can paste the stack trace that I copied, then scroll down to our code, click on the line number, and I'll be taken to the place in the code that is responsible for the excessive memory usage. Mining code is indeed part of our blockchain-based tamper-proof stopwatch that you saw in the UI before. But why does it use so much memory? As you can see, we're using the JavaStream API's map method. And the way this method works is it takes the primitive long ID field and boxes it into a long with a capital L object, which of course needs memory and needs to be garbage collected later. It's actually a very common pitfall when using the JavaStream API. The way we can solve it is by replacing the map method call here with a map to long method call. And this way, no extra heap allocations will take place, and the blockchain-based stopwatch that you're using will not need that much memory. I also have a copy of the fixed version of the application running in my computer. And in the interest of time, let me just show you the charts from a run that I did earlier. Now, if you look at the memory allocation rate chart, then you will see that by changing just one line in the code, we were able to drop the memory needs of our application from more than a gigabyte per second to less than 1 megabyte per second. In conclusion, remember that Splunk's always-on profiler is continuously monitoring your application in the background, capturing stack traces when certain memory allocation events happen, and should you ship code in production that is memory hungry, you just need to zoom into the time window when this allocation behavior takes place, and the flame graph will give you a nice drill down of how much do each of the different parts of your code allocate memory, so that you can easily find the line in code that you need to change.